Welcome to another podcast. In this episode, we're going to be taking a look at what is called a related rates problem. Related rates problems are one of the more important applications of the derivative and specifically the chain rule. Essentially, when you look at a related rates problem, the idea is to determine a specific rate using knowledge of another rate that is related, and this process almost always involves an application of chain rule or other associated derivative rules. So the example that I want to take a look at is a really good example, just sort of demonstrate what the ins and outs of this process are. So the question we're asking is, how rapidly will the fluid level inside a right cylindrical tank of radius r drop if we pump the fluid out at a rate of 3,000 liters per minute? So the first thing that I advise you doing with related rates problems is, and you can do these in either order, but draw a picture and identify the units involved. So we're going to start here by drawing a picture. We have a right cylindrical tank, so its base is at a right angle to the ground. And so here is our tank. And what we're told is that we are pumping water out of the tanks. Let me draw a little spigot here. So the water is flowing out of the tank at a rate of 3,000 liters per minute. Now, what you have to decide is what rate is associated with 3,000 liters per minute. Well, liters is a measure of volume. So 3,000 liters per minute is the change in volume with respect to time. In other words, how is the volume of it changing over time? And the question is, should this be positive or negative? Because we're losing volume, that should be a negative amount. So the first rate that I can figure out in the problem is dV dt, the change in volume with respect to time, and it's given by negative 3,000. Similarly, there's a certain amount of fluid inside the tank, and this fluid changes over time such that the height is decreasing. So how rapidly would the fluid level drop? So we're looking at the change in the, let's say, the height, dH dt, the change in the height of the fluid level. That's what we're trying to figure out, is how rapidly does this height drop as a function of time. Okay, so given that, we need some equation that relates the volume of a cylinder to the height of a cylinder. And so if you recall from geometry, the equation for the volume of a right cylindrical solid is pi r squared h, where h is the height, r is the radius, and v is the volume. Now, anytime that you have a equation like this, you should make sure that the units match up on both sides. And what I mean by that is, what we're given in this problem is that the volume is in terms of liters. So I'm going to draw in the units along with the components here. Pi times the radius squared. The units on the radius are r, and since this is in terms of liters, typically we think of radius as a distance of measure, and so it would be measured in meters since volume is in liters. Tank of radius r meters, so we know this is in terms of meters. And since it's r squared, the units here are meters squared, times the height, which is also in meters. So if I'm looking at this, I know that the units on the left are in terms of liters, which means the units on the right should also be in terms of meters, but right now all I have is m squared times m, or cubic meters. So cubic meters and liters don't match up as units, but there is a simple conversion here. Hopefully we recall that 1 cubic meter is equivalent to 1,000 liters. So the idea here is if I wanted, in other words, there's 1,000 liters for every 1 cubic meter. That's a good way to think of it. If I want to update this formula, the formula that I should be using here is really 1,000 pi r squared times h, because 1,000, the units on that are liters per meter cubed, and then the units on pi r squared h we discovered were meters cubed. So liters per meter cubed times meter cubed is equal to liters. And so just make sure that anytime you have an equation like this, that the units on both sides are the same, that they balance out. Otherwise, you may be working with the wrong equation. So our formula that we're going to go with here is volume is equal to 1,000 pi r squared h. And this is the formula that's going to allow us to relate dV dt with dH dt. So I'm going to have to take a derivative. So if I take a derivative with respect to time, then the derivative of this becomes dV dt equals 1,000 times pi r squared. R doesn't depend on time, but height does, so height becomes dH dt. And I want to solve for dH dt, so if I take and write dH dt, it's equal to dV dt divided by 1,000 pi r squared, and dV dt is negative 3,000. So we get negative 3,000 here times this. And as we cancel values and simplify here, this gives negative 3 over pi r squared. And so the rate at which the height is changing is a function of the radius. So as the radius gets bigger, obviously the height is going to change more slowly, but the height is decreasing, which we would expect, decreasing by a rate of, now what are the units here? That's the big question. The units in this case are, so the height is decreasing by 3 pi r squared meters per, and it depends on whatever my units for time are. In this case, my units for time are minutes. So time is in terms of minutes, so meters per minute. So this is the rate at which the height is decreasing in that cylinder, the height of the fluid. All right, this is our first sort of example of related rates. We're going to do another one of these problems in another video, so I encourage you to take a look at that. The problem in the next video is going to be a little bit different. We're going to approach it from a different sort of point of view, just to show you that this concept relies on a lot of different areas of mathematics that you've done previously, like unit analysis and geometry and algebra and calculus. All of them kind of have to be used to be able to figure out the answer to some of these problems. All right, thank you for watching.